Welcome back. In this lecture, we will look at an important aspect of fuel cell that is of practical relevance. How much of current is drawn from a fuel cell? With that, the voltage that is delivered from a fuel cell also changes, and this kind of current voltage relationship is often referred to as the polarization curve of a fuel cell. In this, we will look at one part of the polarization curve, which can be reasoned from thermodynamics. So this is the polarization curve. What is shown here is the polarization curve from three different kinds of fuel cell. Alkaline fuel cell, which operates at 82 degrees centigrade, proton exchange membrane fuel cell, which also operates at around the same temperature, 80 degrees centigrade. Both these things are in some ways similar. Okay, so this is the polarization curve for alkaline fuel cell. We are plotting the potential in the y-axis and current density in the x-axis. So as opposed to these two fuel cell, solid oxide fuel cell operates at much higher temperature, which is 800 degrees centigrade. The composition here is also sort of similar. That is, for alkaline fuel cell and solid oxide fuel cell, you're only supplying hydrogen, oxygen. But for proton exchange membrane fuel cell, oxygen is supplied via air. So there is some small difference in pressures. So what is shown here is that there are different segments. For example, at what is the potential that one may get from fuel cell when there is no current drawn. Okay, so something like an open circuit potential. And we have also indicated that there is some parts which are explained based on kinetic reasons, that is the electrochemical reaction kinetic reasons, and there is an ohmic part and mass transfer part. We'll go into these things in subsequent lecture, but in this lecture, we will look at this part alone. See, we already know how to think about the open circuit potential. The potential that you can obtain from a fuel cell depends upon the delta G of the relevant reaction. Here you have an exothermic reaction. Therefore, fuel cell is a device that provides you electrical potential. So based on this relationship, you can get the potential. However, the potential seems to be different, even though the composition is more or less the same. And there are two main reasons for differences in potential, open circuit potential for the three different fuel cell whose data is provided here. The first reason is the variation of standard potential because of the variation in temperature. So we have standard electrochemical potentials usually given at a particular temperature and pressure. But when you want to understand the temperature, how temperature affects the standard potential, the way to think about that is to think through the free energy changes. The dou G by dou T at constant pressure depends on entropy. This is a simple result from your thermodynamics courses. So the main determinant of how free energy changes with temperature and consequently potential changes with temperature depends upon entropy changes. So you have hydrogen, oxygen, which is always at vapor state. Below 100 degrees centigrade, the product water would be liquid. Above 100, it will be vapor. Therefore, the configurational entropy will be very different. Configurational entropy of water will be very different below and above 100 degree centigrade, that has a significant effect on the potential. If you're unsure of this statement on what exactly do we mean by configurational entropy, I would strongly urge you to go through this particular lecture, this in a separate playlist on thermodynamics UG classical continuum. In that, there is a lecture on brief introduction to microscopic formulation of entropy. In my opinion, it is very, very important to understand entropy through a microscopic formulation. That is in my opinion, the most ideal way to think through entropy. So please go through this entropy if you're not sure about what exactly do we mean by configurational entropy. Moving on. So once we know how free energy changes with temperature, we just substitute the formula for free energy in terms of potential. You can get how the potential changes with temperature. Just a simple rearrangement would give you this formula. So what does this tell us? What is if you know the potential at some standard condition, which is obtained from tables, you can get the potential at some other temperature. So further manipulation, fairly simple manipulation from your thermodynamics, will also provide you another expression. Typically, there are two ways of looking at the variation of potential with temperature, either via this formula or via this formula. Again, all these quantities, like let's say the delta H, will also be available from standard tables. So you have to look at the particular reaction you are utilizing in your fuel cell. From those reaction enthalpies, you can get to the variation of potential with respect to temperature. So if we, using such a formula, you can get this change in potential with respect to temperature. So this is obtained from this equation. You can have slightly more accurate model, which doesn't really significantly change the way potential significantly change the potential. So we can stick to this equation. So what does this tell us? Okay, so when you look at a solid oxide fuel cell which operates at much higher temperature, what is expected just from your thermodynamics is that the potential will tend to decrease with temperature. And the main reason for this decrease between, let's say, the PEM low temperature fuel cell that is operating below 100 degrees centigrade and above 100 degrees centigrade is the entropy of water. In general, you can get the variation via this particular formula. So one aspect of the polarization curve, that is the temperature dependence at, let's say, when you're not drawing any current, that is the open circuit potential, can be rationalized via simple thermodynamics. But in addition to that, you, even taking that into account, you don't see all the variation that is between these three fuel cell. All the variation cannot be captured just from this formula, right? Going by that, you should, let's say, solid oxide fuel cell should have much lesser potential compared to alkaline fuel cell or PEMFC. So the other aspect because of which the potential, open circuit potential, depends upon is the composition. The composition of the reactants that you utilize and the products, of course, that also determines the potential. We have seen this form of equation when we looked at the electrochemical thermodynamics. So please refer to those lectures to rationalize this formula. With this, we can get to the other variation. The once you take into account the different composition of solid oxide fuel cell, the composition, you have to correlate these formula with these compositions. That will give you the open circuit potential to be 1.1 for alkaline fuel cell. The composition is utilized is different, so that would give a different potential, and so on. So the main take home message is there are two main reasons for the variation of open circuit potential between different fuel cell. First variation is temperature. The second reason for variation in open circuit potential is the composition. Between these two parameters, temperature and composition, we can rationalize behavior when the current is not drawn or the open circuit potential. In the next lecture, we will look at the rest of the polarization curve, which depends upon the electrochemical kinetics, ohmic laws, and mass transfer effects. Thank you.